Hello class, welcome to your lecture. Please pause your video recording so that you can complete your bell work for today. Dalton's atomic theory consists of two major postulates. Matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change or a chemical reaction. Number two, an element consists of only one type of atom, which has a mass that is characteristic of that element and is the same for all atoms of that element. Now remember, an atom consists of all the subatomic particles of a certain element. Part 3, Dalton's atomic theory. Atoms of one element differ in properties from atoms of all other elements. That's what makes elements so unique. Number 4, a compound consists of atoms of two or more elements combined in a small whole number ratio. In a given compound, the number of atoms of each of its elements are always present in the same ratio. For example, when we think of water, H2O, that is a compound consisting of two hydrogen atoms and one oxygen atom. Number 5, atoms can neither be created nor destroyed during a chemical change, but instead rearranged to yield a different type of matter. For example, hydrogen is different than oxygen, but when combined together into a compound, they yield water. It's no longer hydrogen and no longer oxygen. No hydrogen was destroyed and no oxygen was destroyed, yet a different type of matter was created through a chemical reaction. Another example of a compound is copper-2 oxide, where we have copper and oxygen combined to form copper-2 oxide. The copper, brown spheres, and oxygen, red spheres, combine together in a 1-to-1 ratio. These two elements were combined, and you can see their reaction and the rearrangement of their atoms to form a compound containing both copper and oxygen instead of their original elementary components. The basic concept of Dalton's atomic theory provides a microscopic explanation of the many macroscopic properties of matter that you've already learned about. If atoms are neither created nor destroyed during a chemical reaction, the total mass of matter present when chemicals change from one type to another will remain constant. Therefore, when you're adding the relative amounts of oxygen, hydrogen, and carbon in a compound containing carbon, oxygen, and hydrogen, their masses should not be changed just because you created a chemical reaction. The law of definite proportions, or the law of constant composition, all samples of a pure compound contain the same element in the same proportions by mass. For example, sample A, carbon has 14.82 grams and hydrogen is 2.78 grams. Then you can have the mass ratio where you can create a ratio of carbon to hydrogen where we can reduce to get each number where there is just one hydrogen atom. So basically you can reduce the fraction from 14.82 to over 2.78 to yield the carbon to hydrogen ratio simplified into 5.33 grams of carbon and 1.00 grams of hydrogen. The same can happen in the carbon to hydrogen sample B. 22.33 grams of carbon to 4.19 grams of hydrogen yields the mass ratio of 5.33 grams of carbon to 1.00 grams of hydrogen. The law of multiple proportions states that when two elements react to form more than one compound, a fixed mass of one element will react with the mass of the other element in a ratio of small whole numbers. For example, compounds containing chloride and copper. A green solid contains 0.558 grams of chloride to 1 gram of copper. The brown solid contains 1.116 grams of chloride to 1 gram of copper. Therefore, when you make a proportion of the green solid to the brown solid, you would get 1.116 grams of chloride over 1 gram of copper over 0.558 grams of chloride to 1 gram of copper. Compared to the copper chloride compound in A, where copper is represented by the brown spheres and chloride is represented by the green spheres, the copper chloride compound in B has twice as many chloride atoms per copper atom. you can see here that the green compound is higher in chloride, making it more green, whereas the other one has less chloride. Just to review, as this is a very important concept that we will carry with us through chemistry. When the number of protons and electrons are not equal, the atom is electrically charged, and this is called an ion. Charge of an atom, or the ionic charge, is equal to the number of protons minus the number of electrons. Now, if you remember, protons are positively charged, electrons are negatively charged. So basically, the charge of an atom is the net charge of the ion. Atoms and molecules acquire charge by either losing or gaining electrons. When you lose something negative, you become more positive. So don't let this confuse you. When you lose 2 electrons, you have a positive charge of 2. When you gain 2 electrons, you have an electric charge of -2. So when you always have to think of this in terms of how many electrons did you lose, and remember that each electron has a negative charge of 1. A cation versus an anion. An anion is a negatively charged ion, right? So if it's a negative charge, it must have gained negativity or gained electrons. That's a very important concept to remember. Anions have gained negative charge and therefore have gained electrons. An atom that has a positive charge is called a cation. Because it has a positive charge, that means it has lost negative charge. Negative charged electrons, that is. We have lost negativity, creating a positively charged ion called a cation. Let's go over an example. A neutral oxygen atom, Z equals 8, has 8 electrons. If it gains 2 electrons, it will become an anion with a -2 charge. It starts with 8, then you gain 2 electrons. When you're gaining 2 negatives, when you already have 8 negatives, that becomes -2. I'm sorry, let me go over that again. A neutral oxygen atom, Z equals 8, has 8 electrons. If it gains 2 electrons, it will become an anion with a -2 charge. You have 8 protons, and now you're having 10 electrons. Because you've added 2 negative electrons, you get -2. 8 would be the number of protons. Originally, you have also 8 neutrons. But when you, 8 protons, and originally you also had 8 electrons. When you gain 2 more negative electrons, you go from 8 electrons to 10 electrons. So therefore, your charge is -2 because you have 2 more electrons than you do protons. Let's go over the cation. A neutral sodium atom, Z equals 11, has 11 electrons. If this atom loses 1 electron, it will become a cation with a +1 charge. You start with 11 protons and 11 neutrons. You gain an electron, or you lose 1 electron. Goodness. Let's start over again. You have Z equals 11, which is 11 positively charged protons and 11 negatively charged electrons. If you're losing 1 electron, you now only have 10 electrons. 11 minus 10 gives you a +1 charge. We will go over more examples of this later. Isotopes are elements that are going to be similar, but they have a different number of neutrons. So we talked about ions having different number of electrons. Now we're talking about isotope having different number of neutrons. All isotopes of the same element have the same number of protons, but their neutrons are different. For example, magnesium exists in nature as a mixture of these 3 isotopes: magnesium-24, magnesium-25, and magnesium-26. All of these isotopes have 12 protons, but the number of neutrons are different. Hydrogen, for example, exists as a mixture of 3 isotopes in nature. We have hydrogen with 0 neutrons, hydrogen with 1 neutron, and hydrogen with 2 neutrons. If you notice, the number of their protons does not change, and neither does their atomic number. We can see their mass from these measurements right here. We see their natural abundance on the right-hand side. We will be learning how to calculate natural abundance, which equals their percent of that specific isotope in nature. Atomic mass, which you have already learned about, is equal to the single atom therefore the atomic mass of a single atom is about its mass number. That is how we are calculating atomic mass. However, most of these elements actually in nature, as we just learned in isotopes, exist as a mixture of two or more of different amounts of this element. So we saw that all of these for hydrogen are mixed in nature, whereas the protium has the most percent in nature. There are trace amounts and small amounts of the other two isotopes in nature. The same with this example of magnesium, where they all have the same number of protons, but their neutrons are different. To find the atomic mass, we average out the mass of their isotopes in nature and do an average. So the periodic table that lists the atomic mass actually is listing the average atomic mass of all isotopes that are present in nature. For instance, the element boron is composed of two isotopes, 19.9%, which is its percent abundance of boron-10 with a mass of 10.0129 AMU. The abundance of boron-11 is 80.1% with a mass of 11.0093 AMU. To find the atomic mass, which is listed on the periodic table, we would average the two masses. So you would take the percent abundance in decimal form, remembering you have to multiply a percent by 0.001 to get it out of a percent into a decimal. So 19.9%, you move the decimal two places to the left, would become 0.199 times its AMU, which is 10.0129. That would get you the average abundance in nature and its average mass, plus the percent abundance of boron-11, which is 80.1, move the decimal place twice, becomes 0.801 times 11.0093. That would get you the average mass of boron, and that is the number that you see of boron on your periodic table. The way that we find mass or average abundance to find our isotopes in nature is via mass spectrometry. The occurrence of and natural abundance of isotopes can be experimentally determined by using this instrument called a mass spectrometer. The sample is vaporized and exposed to a high-energy electron beam that causes the sample's atoms to become more charged, and typically they lose electrons. These cations are then separated by their mass and charge. Now, if you don't understand the whole process of mass spectrometry, that's okay. The important part is looking at this table right here. We see that there are different isotopes of zirconium. We can see that it has zirconium 90, zirconium 91, Zr 92, 94, 96. What you would do is you would take the percent abundance of each of these. So of our Zr 90, we would take 90, and then it's about 50%. We can round here, so it would be 90 times 0.5, because you have to move the decimal of a percentage 2 times to the left. 91 times, we'll say this about 10%, so 91 times 0.1 plus 92 times, I would say this about 15%, 94 times about 15%, and 96 times about 5%. That would give you the atomic mass of zirconium via the percent abundance route. Now, I can't tell you that my estimates are going to be exactly equal to what we find on the periodic table, but this is just an example of how to use a mass spectrometry table to be able to find the percent abundance of each of the isotopes and to find the average atomic mass, which is what we see on the periodic table, of each element. that will conclude our lecture for the day. Please pause the lecture as is coming an exit ticket. Go ahead and pause the screen. Here's your exit ticket. You are to find the average atomic mass for element Q using its percent abundance as follows. Find the average mass. If you guys have any questions, as always, feel free to reach out. We will have more practice questions on mass spectrometry and percent abundance upcoming in next week's modules. Have a great rest of your day. I'll see you guys soon.